Have you ever stopped to wonder how your computer understands something as complex as a photo or a song or even the sound of your voice? I mean, it all comes down to a language that's way, way simpler than ours, a language of simple on and off switches. So, how do our rich, complex ideas get translated into the simple, binary world of a machine? Well, let's find out. So here's the roadmap for our journey today. First, we're going to look at the huge difference between our numbers and the computer's switches. Then we'll actually learn to speak its native language, binary. After that, we'll see how it does math, tackle the really tricky idea of negative numbers, and finally, we'll see how it encodes our entire world. Okay, let's dive right in. At the heart of everything is really just a translation problem. You see, we live in one kind of numerical world, and computers live in another, much, much simpler one. And here's the core of that difference. Our world is base 10. We've got 10 different digits to play with, 0 through 9. A computer's world, on the other hand, is built on billions of tiny little switches that can only be off or on, low voltage or high voltage. So it only has 2 digits to work with, 0 and 1. And that's the base 2 system. Now, the way we understand our numbers is all about position. Think about the number 7,243. That 3 on the end is just 3. But the 2 isn't just a 2, it's 2 hundreds. And the 7 is 7 thousands. Each spot is a power of 10. We learned this so early in school that we don't even think about it anymore. It's just second nature. And what's so cool is that computers use the exact same idea. The only difference is that their positions are powers of 2, not 10. So when a computer sees the binary number 1001, it's not thinking 1001. It sees 18, 04s, 02s, and 11. You add that up, and it's the number 9 in our world. It's the same principle, just a different base. Okay, so now that we've got the basic grammar down, let's get a little more fluent. We're going to really dive into the native language of computers and even learn some helpful shortcuts that make it easier for us humans to read and understand. So just to make it official, the binary system, or base 2, is the native tongue of every single digital computer out there. Every piece of information, every photo, every email, every website is ultimately represented by combinations of just these 2 digits, 0 for off and 1 for on. It's a direct reflection of the physical state of transistors deep inside the processor. But here's the thing. Long strings of ones and zeros are an absolute nightmare for our human brains to look at. It's just a jumbled mess. So to deal with this, programmers came up with a kind of shorthand. Now these systems, like octal and hexadecimal, they're not for the computer. The computer doesn't care. They're for us. They let us group long binary numbers into nice, tidy chunks that we can actually read and work with. All right, now we're getting to the really fun stuff. We know how computers can store numbers, but how do they actually do anything with them? Let's take a look at how they handle the most fundamental operation of all, addition. It turns out binary addition works exactly like the math you learned in elementary school. You go column by column from right to left. The only new rule you have to learn is that in binary, 1 plus 1 equals 10, which is just how you write the number 2. So you write down the 0 and you carry the 1. See? Same old carry the 1 trick. You just apply that simple logic and boom, you get the right answer, 1000, which is binary for 8. So computers can store numbers, and they can add them. But this opens up a brand new puzzle, a really interesting one. A computer's entire world is just on and off. There's no built-in idea for less than nothing. So how in the world does it handle negative numbers? Yeah, this is the real head-scratcher. Without a special symbol for minus, how can a machine possibly know the difference between, say, +5 and -5? It needs a system, some kind of clever convention. So one of the first ideas people came up with was something called ones complement. The process itself is super simple. To make a number negative, you just flip all its bits. Every 1 becomes a 0, and every 0 becomes a 1. It's a really straightforward first attempt, but it's got a hidden flaw. And that brings us to the modern, elegant solution that pretty much every computer uses today. It's called two's complement. It's a simple 2-step process. First, you do the ones complement. You flip all the bits. And then you just add 1 to that result. Now, that tiny extra step might seem insignificant, but it's the key that makes the entire system work perfectly. So why is two's complement the undisputed champion? Well, as you can see here, the other methods created this really bizarre problem. They ended up with two different ways to write the number 0, a positive 0 and a negative 0. And for a machine that runs on pure logic, that's a total disaster. Two's complement just brilliantly solves this. There's only one single, unambiguous way to write 0. Clean, simple, perfect. But here's the real stroke of genius. Because it uses two's complement, a computer doesn't need a totally separate, complex circuit just for subtraction. If it wants to calculate 5 minus 3, it just takes 5 and adds it to the binary for -3. Subtraction becomes addition. From an engineering perspective, this is incredible. It makes the physical hardware of the processor dramatically simpler, cheaper, and way more efficient. Okay, for our final section, let's zoom out a bit. We've totally nailed down how to handle numbers, both positive and negative, but our world is so much more than just math. So how do these simple patterns of zeros and ones represent everything else, every letter you type, every symbol, every single emoji on your phone? Well, the first major attempt to standardize all this was called ASCII, and it set aside 128 unique binary codes, which was enough for all the characters needed to type in English. ASCII was a huge deal. It was like a universal dictionary for computers. It meant that a capital A, which was assigned the number 65, would be understood as a capital A by any computer anywhere. It created this common language for text, giving a specific binary pattern to every letter, number, and basic symbol you'd find on a keyboard. But obviously, the world speaks a lot more than just English. As computing went global, we needed a much, much bigger standard. So, enter Unicode, a system designed to handle over 1 million different characters. That's quite a jump from 128. The goal of Unicode was incredibly ambitious to create one single standard for every character from every language on Earth. We're talking Chinese, Arabic, Cyrillic, ancient scripts, and yes, every single emoji. It's the reason you can get a text from anywhere in the world and your phone knows exactly what to display. It's what makes our digital world truly universal. And that really brings our journey full circle. From that incredibly simple idea of just on and off, we've built a system that can calculate, communicate, and contain pretty much all of human knowledge. It's a powerful reminder that underneath all the amazing complexity of our digital lives lies a language of stunning simplicity. Just think about it. Every photo, song, and message you've ever sent is just a long line of switches, flipped in the right order.